All right, guys, it's later on in the evening, and clearly we're slumming it at this point, but I wanted to go ahead and get another video in about some of this stuff that we're doing in the conjugated pi systems. And so we just finished talking about molecular orbital theory and how we use molecular orbital theory and linear combination of atomic orbital and all of our super awesome linear algebra skills in order to construct molecular orbitals from atomic p orbitals. In other words, we learned the patterns and we learned about how to use those patterns to successfully and consistently draw the molecular orbital diagrams for a series of conjugated pi orbitals, and think about them energetically, and then think about the phasing of the different orbitals. That's really all we did. And so that's just the first step. And what we're going to do is we're going to use that to explain some stereochemistry of some different reactions. And so what I want to do now is I want to go over a particular set of reactions where that is helpful, and those are electrocyclic reactions. And so I'll show you, going back to the molecular orbital theory, how we use that in order to explain the stereochemical outcome. Now, at the end of the day, you're going to be faced with a choice. Your choice is know the molecular orbital diagrams, know how to apply that to stereochemical outcomes, bam, and then you can solve any problem. Or you can memorize a certain couple of series of reactions and use the memorization skills to do the same thing. But then if you start to get some problems that ask you to explain why, now you're just going to miss those. And so that's the organic chemistry choice of your lifetime, is always memorize the stuff that'll get you the answer to most of the questions, except for the ones that ask you why. Then you're going to have to struggle. But let's take a look at those orbitals. Let's get right into that, and I'm going to start up my screen. All right, so this is where we left off. This is where we left off. We were talking about molecular orbital theory, and why is this upside down? Oh man, I'm in bad shape here. Good thing I can turn it right side up. Look at that. The wonders of modern technology. So this is a big mess. This is a mess of a drawing that depicts how we can use these patterns, especially the patterns of remembering how many nodes are at each energy level in a system of molecular orbitals, and then using that and along with some other quick patterns to draw a series of orbitals. Now, what I want to do now is use this and focus on the HOMO and the LUMO in the ground state, and think about how that works out in the excited state. Now, remember what we said before was that in the ground state, this is the orbital that is the highest occupied molecular orbital. And at the end of the day, chemistry happens between HOMOs and LUMOs, between the highest occupied molecular orbitals of one thing and the LUMO of another thing. In other words, where can electrons go? They can go to the lowest unoccupied molecular orbitals. Where do they come from? Well, they'll come from the highest energy electrons, the highest energy occupied molecular orbitals. So that's certainly one way to think about chemistry. Now, that's the ground state. But when we react a conjugated pi system or expose it to UV light, then we're going to get an excitation of the electrons. And the electrons are going to, one way to look at that is to say the electrons move from the ground state to the very next highest energy orbital. And this becomes an excited state. And so now it's a little bit different. In the excited state, this is the orbital that is now the highest occupied molecular orbital. So one could say this is where the chemistry is going to take place. And we've got a great experimental evidence that's saying, yeah, okay, well, the way that we're going to line up these orbitals, the way they're going to rotate in order to form bonds is going to be such that the phasing of the orbitals are the same, so they can overlap. That's the word we're going to use, is overlap. And these pictures from molecular orbitals line up real well with what actually happens in the lab. And so I want to just remind you what these pictures look like. And so this is where we started off yesterday, or this is where we left off in the last video, was with this particular drawing. And I also want to draw your attention to the corner where we are looking at the drawing from the previous system. So the picture that is larger is the 6-electron system. The picture that is smaller is the 4-electron system. And I want to remind you that when we look at the 4-electron system, we have the same sort of situation with the different orbitals. We'll have the same situation with the HOMO and the LUMO. And so if I were to think about the 4-electron system, just to point it out, that in the ground state, this is the HOMO in the ground state, and in the excited state, that's going to be the highest occupied molecular orbital. And so there's an important thing to look at. In the ground state, in the 4-electron system, the phasing at the atoms on the end are out of phase. In the excited state, the phasing is in phase on the outermost atoms. Now, if we come back to the big picture of the 6-electron system, and we think about the outermost atoms, in the ground state, they're in phase. In the excited state, they're out of phase. And we're gonna go back to this picture to sort of explain some chemistry here in a second. So I'm gonna put that off into the corner real small so that we can remember what's going on. Okay, and so I said we're gonna talk, why does it matter? Well, because we wanna use this to explain. Again, questions in organic chemistry often come in broadly in two different forms. Can you regurgitate the answer? Can you explain why it happens? And regurgitating the answer is certainly fine for most students, but if you really want to attain that high level of understanding, that high level of achievement, then you really need to be able to tell me the answer and tell me why it is that way. And so let's think about some reactions. The class of reactions that I want to discuss right now are called electrocyclic reactions. And what I want to do is I want to make sure that I'm drawing a nice picture, not some of my usual slop. But if I start out with a conjugated system like this, or if I start out with a conjugated system like this, then I can do a reaction, and the position of the equilibrium is different based on the actual molecule. And so what I won't, let's not worry about the relative position of the equilibrium at the moment, but let's just understand that I can react these two systems with light and heat. I think the relative position of the equilibrium is more like this for this one, and more like this for this one. But again, let's not worry about the relative positions of the equilibrium. Let's just make it obvious that it's an equilibrium. And if I react these two systems in one of two ways, either by reacting them with heat or exposing them to UV radiation, then I can get a ring closing. Same thing with the mechanism here. So what this would do would be to form a 6-membered ring. It would still be conjugated. And in this case, it forms a 4-membered ring with only one double bond. Great, that's awesome. Those are really cool reactions, so cool. Except you know that these are just the basic reactions with no sort of groups that are added on that can complicate the stereochemical outcome. So what I want to do now is get to that piece. Let's complicate the stereochemical outcome a little bit. And so if I were to think about what would happen if I did the same reactions, I'm actually going to go ahead and get rid of this now. If I do the same reactions But now I want to add a substituent, a group at the end. So there's one of two possible versions where this could take place. I could have one where the two groups, and I'm just going to go ahead and write in some CH3s, where the CH3s are, remember, those carbons at the end, they're going to be sp2 hybridized. That's a trigonal planar geometry. And so if it's a trigonal planar geometry and we force those two bonds to sort of, the two double bonds, these double bonds, oh boy, these double bonds, we force them to be in the same plane, then what we can say is that the CH3s either point away from each other, or the other possibility is that they point towards each other. And I'll show you what I mean by that. And I shouldn't say towards each other, because that's not a correct description. What I should say is they point in the same general direction. These do definitely point away from each other, and they point in opposite directions. If we were to use the whiteboard as a descriptor, the molecule on the left has one pointing up and the one pointing down, if you want to use the whiteboard as being on a vertical wall. So in this, the other case is that the two CH3 groups could point in the same direction, CH3. Now, there is another case that I'm not that I just want to show you real quick, but that actually doesn't result in a reaction, is what if they were like this? This is not a situation that we have to worry about. So these are the two situations that we have to worry about. Now, what happens here? Now, if I react this thing with heat, then I get a particular stereochemical outcome. I get the situation where these two groups, these two CH3 groups, end up being cis, pointing in the same direction. What's cool is if I do the same sort of reaction with this other molecule, but I do it in the presence of UV light, I also get cis stereochemistry. Now, remember, I think ultimately the stereochemistry of the reaction equilibrium of the next set favors the ring opening and not the ring closing. I'm going to nonetheless show it from the perspective of the ring closing, just to talk about it from a stereochemical perspective. If I have a four-membered ring, or if I start out with a 4-electron pi system, and they point in the same direction, or if I start out with a 4-electron pi system and they point, and I said that wrong, these point in the same direction, both pointing up. These on the left, they point in the opposite direction. One points up, one points down, from the perspective of the whiteboard being on a vertical wall. Okay. Now, what we get is a ring closing. Remember, I said that the ring closing is not actually favored from the equilibrium standpoint, but we get a ring closing that looks like this. We get one up and one down. So the stereochemistry ends up being trans, and this is also in heat. This is also in H nu. Now, if I were to do this situation, have this reaction, one of these days I'm going to learn how to copy really quickly in this app so that I don't have to do all this drawing again. But if I reverse the situation, showing the same conjugated system, but now I want to show UV light there and heat there, then I get the transversion. Now there's one more set to draw. I'm going to just shrink these down just a little bit so I have some room to draw that next set. If I take this 4-electron system and I start out with things going the same direction, if I take this 4-electron system over here, have them starting out in a different direction, do the same type of reaction, heat on the left, H nu on the right. Then I get the trans stereochemistry at the end of the day. Or excuse me, the cis stereochemistry at the end of the day. All right, so here's your first choice. I'm going to show you some reactions like this on exams and quizzes. I'm going to have different groups. Remember, I'm just showing you CH3 groups. They certainly could just be R groups, in which case you'll have to deal with them appropriately. They could be the same, they could be different. Again, you'll have to deal with them appropriately. Your first option is to memorize this chart. Well, your second option is to understand why this is, or to use the power of molecular orbital theory to explain the outcome of these reactions. And so if we were in a classroom, I'd put these on a reaction board and say, here's some reactions that you have to know. But then at the end of the day, on the reaction board, we don't explain why. And so I'm going to put this in the corner and keep it expanded a little bit so that we can still see what's going on. And I want to go back to the molecular orbital theory and explain why. How can we use molecular orbital theory to explain what's going on? And so what I want to do is I want to switch back to a different projection. I think this is called a Hayworth projection. But you know, I'm terrible with my proper nouns. At any rate, what I want to do is I want to project this molecule in 3 dimensions, this conjugated system in 3 dimensions. And so these 2 bonds are coming out towards you. And now I want to just, I'm going to use my red or my blue to just indicate I've got a conjugated pi system here. I'm going to do that momentarily. I'm going to get rid of it in just a second. But I want to correlate this to the situation where I have a molecular orbital diagram like this. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And so I'm gonna get my little eraser out. I'm gonna erase the conjugated double bonds. So I want everyone to remember that I am talking about a conjugated pi system, because ultimately what I want to do is I want to line up on each of these atoms. I want to line up the correct picture of the orbital. Now, before we do that, let's put the groups on there. Well, if the groups face different directions, like in that very top example, and remember they were CH3 groups in the example, then once I've moved them from being parallel with the whiteboard to flipping up and sort of sticking out of the whiteboard, then the groups are no longer facing up or down, but really the best thing is to say they're facing different directions. And so when I put the groups on this framework, I want to make sure that I put them in different directions. The other option, of course, was when the groups pointed essentially in the same direction. the way that I would show that is to show it like this, pointing in the same direction. And so what I want to do is I want to use the molecular orbital diagram to recall the HOMO and the LUMO. So I'm going to draw it just a little smaller than I had set up there for a second. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And let's recall, where are we in the molecular orbital diagram for the 6-electron system? We're at the HOMO and the LUMO. And this is going to be the ground state. So in the ground state, I have 2 electrons here. And that's the frontier orbital. That's the lowest or the highest energy occupied molecular orbital. So remember, that means there's two orbitals lower energy that we're just not going to show. So if you're confused, go back to the previous video, look at the set of molecular orbital theories. We're only focusing on the HOMO and the LUMO of the ground state at the moment. So this is the 3rd orbital up. That means there's 2 nodes there, and this one is going to be the 4th orbital up. There's going to be 3 nodes with this one. It's 1, 2, 3. It's important to remember where the nodes go. Now, it doesn't matter what phasing you start with, but I think by convention, we've been starting with blue. And so let's line that up like this. Let's do blue. So that means it's blue here. It's blue up here. It's blue up there. And then let's color it in, because that's such a good time coloring it in before. Maybe I should just start with the bigger marker next time. Filling in these full color diagrams, because if you have the technology, boy, it sure makes them pretty happy. I've already figured out why I don't start there. That one, this one, let's try to do this one. Yeah, that's looking pretty good. Okay, so now we've got the diagram. Right. And so now what we want to do is we want to take those same 6 orbitals, or the same set of molecular orbitals, and place them along this ring, or this proto-ring before the ring closing actually happens, and line them up and to see how they would react. And so remember that what we're going to do is we're going to take this and this one to be the atoms at the end, right? And everything else sort of wraps around. 1, 2, 3, 4, 5, 6, wrapping around. So in the case of the ground state, I'm going to have a blue orbital here, a blue orbital here, a blue orbital down here, a blue phase down there, and then the blue phase is up again. And I want to just expand it out just a little bit, because remember, they're connected, they're lobes. So I'm going to draw some crude lobes connecting them together to remind you that what I'm looking at is this set of orbitals. Okay, but it's okay for now to draw the different phases the way they are, and it'll help us look at the explanation a little bit better when we imagine the orbitals lining up to overlap. Okay, well, if I want to make a ring, then this is what we're saying. We're saying that molecular orbitals, in order to form single bonds, would have to then face each other. They would have to point towards the internuclear axis. We are creating a sigma bond from a pi bond. So the pi bond has to go from perpendicular to along the axis. The other thing that we're saying is that they have to match in their phasing. And you can go and look up some physics videos on YouTube, and maybe there's a guy out there that'll explain to you why there have to be the same phase. But since this is organic chemistry, We're not going to do that. We're just going to say it can be shown that the orbital phasing has to match. Okay, and so what that means is that if I were to imagine the rotation, and it doesn't matter which phase you pick, as long as you rotate them in a fashion that the two phases that are the same color end up being the ones that overlap. So that means I have choices. I can imagine the blue rotating this way and the blue on the left rotating that way. I could also imagine the red rotating up and this red rotating up to form a bond with the red lobes. Either imagination is fine. I'm going to stick with it this way for the moment and say that I'm going to end up with the red rotating, in this case, on the left-hand side, it's rotating counterclockwise, and on this side, it's rotating clockwise. And so what I want to do is examine how the groups, what they end up doing, and where their positions are after this rotation is accomplished. So if this thing is rotating clockwise on the right, that means that this CH3 group has to rotate there in order for this group to be in its correct position. The same thing happens on the other side, but the CH3 group rotates the other direction. So now when I draw the structure as it is, when the ring is closed, I'll draw this bond out now specifically. So we're left with a double bond here and a double bond here. Well, what happened to the two CH3 groups? Well, they're pointing in the same direction. Okay, so why is the stereochemistry the way it is? It's because of the rotation of the atoms in where the sigma bond forms requires that the phasing of the individual orbitals forming that sigma bond be matched. And in order for the phasing to match in this case, the rotation must be counterclockwise on the left atom, or clockwise on the right atom, depending on which orbital you pick. But in this case, what we're saying is the groups line up in the same direction. The groups line up in the same direction. The result is that the groups they end up in the same position. Okay, well, what happens then if we're dealing with the other situation when we have H nu? Why does H nu produce different results than heat? Okay, well, recall when I react a molecule conjugated pi system with UV light, I promote the electrons to a different orbital. So now the highest occupied molecular orbital, the one that's doing chemistry, is going to be this orbital instead of that orbital. So since I'm using the topmost orbital as the highest occupied molecular orbital, I then want to change the way that I'm drawing the phasing of the orbitals. Now I have red down here and red up here. That means I have blue down here and blue up there. I'm not going to draw out the rest of the, okay, heck, I'll do it. Here would be blue, 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 red, 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 red. And this is what matches this position there. Now, let's examine the rotation that would have to take place in order for the correct lobes, the correct phases of these lobes to be lined up. Well, remember, it doesn't matter which one we show. I have to have if I want to show the red ones, then from the perspective of the red phase, the orbital of the atom on the left requires a rotation that is counterclockwise, counterclockwise, and the one on the right requires a rotation that is counterclockwise. So in one case, the rotations are different directions. And in this case, they're the same directions. So the rotation in the top case happens when one atom has to rotate one direction, the other atom has to rotate the other direction from the clockwise counterclockwise perspective. The other cases where they have to rotate the same way, counterclockwise both or clockwise both, depending on which lobe you're looking at. So what would that do then? Well, what that means is that this CH3 group would rotate up to that position, and this CH3 group would rotate down to that position. So when I draw the resulting sigma bond in the three-dimensional projection, this guy ends up pointing up, and this guy ends up pointing down. And so at the end of the day, the stereochemistry is explained by which orbitals are the frontier orbitals that are forming the sigma bond, whether it's this set of orbitals and whether it's this set of orbitals. And the same explanation can be applied to the four-membered ring or the four-electron system, but just remembering that it actually favors the ring opening and not the ring closing. The reverse is true for the first set. For the six-electron system, it actually favors the ring opening. And so I'm not going to go through and show you the individual steps to do it for the four-electron system, but it's exactly the same. In summary, what you would do is you draw out the frontier orbitals, the HOMO and the LUMO of the ground state. And that allows you to get the correct phasing for when you're doing the reaction in the presence of heat. Then, of course, then you're using the HOMO of the ground state. Then you think about what it means to do the excited state, to react it with UV light, and then you realize that what was the lowest unoccupied molecular orbital becomes the highest occupied molecular orbital, and then we use that one as the frontier orbitals to create the sigma bond. And then ultimately you place the different sigma bonds around this three-dimensional projection of the ring, and I'll just show you, you don't actually need to have a perfectly three-dimensional perspective. You can do it just like this, and you don't even have to show the phasing of every orbital. You can just show the phasing of the two orbitals that are making the bond, and you can decide to rotate it that way. It doesn't even have to be in full color. So I just use black and white in this case. And then it would ultimately depend on, is the bond going this, are they pointing in the same general direction? Let's see, left, clockwise and counterclockwise. So this one is going this direction, and this one is going this direction. And so now the result in this case would be one pointing down and one pointing up. And so I gave you a quick demonstration of how you would do it in this stereochemistry for the 6-pi system with UV light. And so you can use that same explanation to talk about this one. Actually, this was the one that I just showed you. You can do this one to get the other stereo configuration, and then you can do every single one of them for all the versions of the 4-electron system. But at the end of the day, this is how you explain the stereochemical outcome by using molecular orbital theory. Again, your option is to memorize this chart. You lose all the explanation, and you can't do other problems that that make you write down the configuration of these molecular orbitals. If you do that, though, you can use those molecular orbitals to explain the outcome and predict the outcome of any reaction I throw at you. And therefore, all you really have to do is remember the two basic reactions. And that's that this thing will form a 6-membered ring with a conjugated pair of double bonds, and that this thing will form a 4-membered ring with a single double bond on that side. And you can then just remember that's the mechanism there, and that's the mechanism there. And so you can remember this and be able to explain it from molecular orbital theory, or you can memorize all of this and not be able to explain it. That's your organic chemistry life choice. That's up to you, whatever you think is best. That's it for now, guys. I'm going to leave this video out there. I'm going to get to work on my NMR and IR video, and I'll see you guys later.